Let's look at some applications for characteristics of capacitors in series. So here's some capacitors and their voltages, or potential differences, across each capacitor. How is the potential difference across each capacitor in series determined? Let's come up with two rules. Okay, you can pause here and look at it, but I'm going to go ahead and go through the rules to save us some video time. Rule 1, in series, the potential difference of each capacitor equals the difference across the whole series. So in the first one at the top, I can see that I got 12 volts on the left and 0 volts for the ground on the right. And the capacitors, 8 plus 4, they use up 12. In the middle circuit, I've got 60 volts on the left, I got 20 on the right. That's a difference of 40, and the two capacitors in series in between them is 30 plus 10, it's also 40. And on the last one, I've got 232 on the left, I've got 100 on the right, so that's 132 volts. 72 plus 24 plus 36 is 132 volts. So in series, it uses up the amount of energy between the two ends. The next one to look at is how it's divided up. That is, the potential is the fraction of the potential difference. So the equation would look something like this. I take the total difference of the voltage between the two ends. So for the middle circuit, that would be 40 volts, times 1 minus whichever capacitor I'm interested in, the 5 or the 15 for the middle circuit, divided by the total. So that would be 5 plus 15 for the middle circuit, and that would be the change in voltage on top of the capacitor. So let's look at how that works for each one of these. So if I'm looking at this, here's my example worked out. I can see I've got the one on the left and the one on the right. On the left, I got 12 volts between the two ends, and that's equal to 1 minus 3 microfarads divided by 3 microfarads plus 6 microfarads, or it gives me 8 volts when I'm all said and done. And for the left one, or for the right one, I can see I've got 12 times 1 minus 6 over 9, and that's going to give me the 4 volts. Notice here that when they're in series, the larger the capacitance, the smaller the potential difference across it. Let's look at the middle one, see how that one sets up. It's the same idea. The difference in voltage is 40 volts. So when I'm setting up the first one, I can see I've got 40 times 1 minus 5 divided by 5 plus 15, that's 30 volts. And for the next one, I've got 40 times 1 minus 15 divided by 5 plus 15, 10 volts. And the bottom circuit works the same way. So here's the math for the 4 microfarads. Here's the math for the 12 microfarads, and here's the math for the 6 microfarads. Let's put the rules to the test. Let's determine the unknown voltage, or come up with an expression that can be used to determine the unknown voltage. You can pause here and think about this, and then restart when you're ready to see the answers. So here's the solution. For the top one of the ways to do it is to look at it and think, all right, the difference between the left and right end is 12 volts. So I've got 12 volts to work for. The 30 microfarads is going to get part of that 12, and the 6 is going to get part of that 12. For the 30, it's going to be 12 times the quantity of 1 minus 30 divided by 36. And that's going to give me 2 volts. Now for the next one, for the 6 microfarads, I can do the equation again, and I get 10 volts. Or I could look at it as, oh, there's 12 volts across this little piece of the circuit. The first capacitor uses 2, so 12 minus 2, that leaves 10. So the 6 microfarads would have had 10 volts. Another fine way to solve the problem. For the bottom circuit, if I'm looking at that one's a little bit easier. It's kind of straightforward and more obvious. The difference in the voltage is equal to the starting voltage minus 80 minus 20, and that's going to give me 40 volts. So that's the voltage on the final one. Now let's change up the question a little bit. What is the charge on the unknown capacitor? The charge, not the capacitance, but the charge. So I know on that unknown capacitor, I know I can pick any one of these and see that the charge is going to be 160. So the charge for capacitors in series, a charge on any capacitor, is going to be capacitance times the change in voltage. So for the first capacitor on the left, that's going to be 2 microfarads times 80 volts. So that's going to be 160 microcoulombs. For the middle capacitor, it's going to be 8 microfarads times 20 volts, which is 160 microcoulombs. And it kind of shows what we know, that capacitors in series all have the same charge. So in that unknown capacitor, its charge will also be 160 microcoulombs. Last question. A 30 microfarad and a 6 microfarad capacitor are connected in parallel to a 60 volt battery. After a long while, the battery is removed and one of the capacitors is reversed. The two capacitors are then connected in parallel with each other. What is the potential difference between the ends of the 30 microfarad capacitor? What a crazy question. Remember, capacitors can act like batteries in storing up energy. So that battery in the middle, on the left-hand side in the middle of the circuit, is just putting charges on the 30 and the 6 microfarad capacitor. On the left-hand side, that's like step 1, where the battery is connected. In the middle, that's step 2, where the 6 microfarad capacitor is removed and turned around. So that's what I'm trying to show, is that it's turned around. And on the right-hand side, that's step 3. That's where it's reconnected backwards. So on the left-hand circuit, you can see the positive side of the 6 microfarad is on the left. On the right-hand circuit, the positive side of the microfarad capacitor is on the right. So they switch sides. So what exactly does all this mean? Let me get a little bit of room so I can do some of the math. I know the charge on the top capacitor. I can find that from Q is equal to C times V. So that's 1800 microcoulombs. On the bottom capacitor, same equation, I get 360 microcoulombs. Then if I look at it, when I remove the battery, I can add up the charges on these two capacitors and see what the total charge is going to be. When I add the charges from the circuit on the right, what I'm going to get is 1800 microcoulombs plus a negative 360. If you look at the capacitor, the positive side in this case is my 1800 microcoulombs, and the negative attached to the same wire on the left side is negative 360 microcoulombs because I flipped it around. So when I add them together, I get 1440 microcoulombs. Again, look at the wire on the left. It's positive on the top by the 30 microfarads and negative on the bottom at the 6 microfarads. So the 6 microfarads are negative charges, and the top one has positive charges. So the negative charges and the positive charges, some of those charges, the positive charges, are annihilated, and that's what I'm left with, 1440 microcoulombs. And it's negative just because I flipped that one capacitor around. The total, now let's look at the total capacitance of the circuit, and we can use that to help figure out what's across the 30, although there are a couple other things we can do. So if I look at the total capacitance, it's 36 microfarads, and it doesn't matter if I flip the capacitor or not, it's still 36 microfarads. So the change in voltage across the total circuit is going to be the new amount of charge that I have, the 1440 microcoulombs, divided by the total capacitance of the circuit. So when I do that, I get a total change of voltage of 40 volts. And because everything I'm doing is in parallel, I know the voltage is going to be the same for all the parallel components. So in this case, the answer is 40 volts. It's going to be 40 volts now across the 30 microfarad capacitor, and the question doesn't ask for it, but it's also 40 volts across the 6 microfarad capacitor.